All right, guys, let's go to page 73. Find this lesson 2, please. Page 73. We're going to start now. So yesterday we covered inductive reasoning. And for inductive reasoning, if you think inductive, I want you to look at these 3 words. Those 3 words are connected to this inductive. Basically, just try something. Don't just sit there waiting for it to dawn on you. You have to try. Basically, use examples to come up with some sort of conjecture. Okay? So examples, and that leads you to some sort of conclusion about the examples. So if you see this word conjecture, it's just some sort of conclusion, some sort of idea based on your examples. And this bullet here, you might get asked about that on a multiple choice question. The inductive reasoning does not prove conjecture. It can only demonstrate that that example works in that moment. Okay? This whole idea of mathematical truth and this thing here called proof, this is what leads to what's coming up next. This is deductive. This is like a sound mathematical argument that proves that your conjecture is true all the time. And it's not easy to do. Like mathematicians, like in the universities, like that's what they do. And it's challenging work. Like they try to prove conjectures mathematically. That's what they're good at. I spent some time doing that. It's not easy. I didn't really like it either. Okay, let's talk about a little bit of logic. This logic has a special word. It's called transitivity. You don't need to know that. But we'll see it in a bit here. But let's just try some logic. Susie drops off a film at quick 1 hour photo. Susie dropped off the film at 10. It wasn't developed until 11:15. What can you deduce from this information? That it's not a quick 1 hour photo. Good. So this kind of be like maybe some of the false advertising maybe. Basically, what did they do to themselves? They put their foot in their mouth. What is that? It's when you say one thing and do another. So what's this word that we could use? Starts with a C. Oh, who said that? Very nice. Contradictory or contradiction. Very nice. Contradiction. Okay, so let's jump into the deductive reasoning, which is also called logical reasoning. This is where you're honestly going to look at me like, wow, I can't believe you just taught me that, because it's so obvious and seems so simple, and you will for sure have test questions like this. Every whole number is an integer. 6 is a whole number. Therefore, 6 is an integer. Okay. Do you know what those 3 dots mean? Therefore. So the 3 dots in this triangle is a symbol for therefore, or like hence. Okay. And this can all be boiled down to a simple work with symbols. So A goes to B, and B goes to C, therefore A goes to C. This is called transitivity, and it works for logic. Mr. Lineweber is a liar. Mr. Lineweber told you He's rich. Therefore, I'm not rich, right? There's some really cool stuff on the internet, like these. My son sometimes goes on YouTube. He's like, the best riddles of all time, and he like looks at this stuff. And yeah, there's like logic stuff out there. Like if you're done an IQ test on Facebook or something, they might have some stuff like this. So this kind of stuff would show up on an IQ test. Water freezes below 0 degrees Celsius. The temperature is minus 15. Therefore, the water's frozen, yeah. It is too easy for some. Got your book today? Is it out? Oh, good man. What's in your... Oh. Okay, let's keep going. There's just one last thing on your book on this page, the theorem. And this is like for Christians, they have their Bible. For mathematics, they have their theorems. It's like it's so sacred to them. Like the theorems is what guides the math. So for example, you guys know a theorem. What's a famous theorem you guys all know? Yeah, the Pythagorean theorem, which states that in a right-angled triangle, the sums of the squares of the two legs summed up equals the sum of the square of the hypotenuse. You know that. Exactly. It's a mouthful, but you know what I'm talking about. So let's jump to the next page. Lesson 1, class example 4. We used inductive reasoning to write a conjecture that the sum of 3 consecutive integers was divisible by 3. So you need to know this word, consecutive. It just means one after the other. So for example, 3 plus 4 plus 5. If you add those all up, it should be divisible by 3. Is 12 divisible by 3? Yes. That doesn't prove that it always works. It just works this time. Do another one. 7 plus 8 plus 9. 15 and 9 makes 24. Is 24 divisible by 3? Yes. Does that prove that it always works? No. That's inductive. Today's lesson is on deductive. This proves it works all the time. If you can prove it. Proves it works all the time. If it's sound mathematically, if it's logically true. You don't make any mistakes. So how could you write 3 consecutive numbers? This is something you also must understand. For this consecutive, and put a star by consecutive, and you have to know how to do this. n plus 1, and n plus 2. How would I get the next one? N plus 3. How would I get the next one? N plus 4. Just try it. Like what if n was 3? That would be 3. This one would be, and this one would be 5. Now what happens if you add all those up? That's what we're supposed to do. We're going to add all these up. You have to remember like terms. What's n plus n plus n? 3 n's. And then what's 1 plus 2? 3. So you have 3n plus 3. Okay, so if we simplify this, we get n plus n, which is 3n. Remember, those are like terms. And the 1 plus 2 makes 3. Those are like terms. You might remember that. But we still haven't proved anything. What we can do now is we can factor out a 3. You guys might remember this from Math 10. They have a common factor. What can they both be divided by? 3. And this is the proof. This is the final step in the proof. Because what is n plus 1? That's just some number. And what if you take some number and times it by 3? Is it going to be divisible by 3? Yeah, because you just times it by 3. That number will be divisible by 3. So I'll write that for you. Since n plus 1 is just a number, when you multiply by 3, it guarantees it will be divisible by 3. And don't just sit there. You need to write that. So I'll be patient and I'll wait for you. All right, let's keep going. Let's go take a look at this chart. So for this chart, just bring your attention back on me. I need you, for the first chart, highlight inductive, and for the second chart, highlight deductive. This class example should demonstrate to you the key differences in inductive and deductive. For inductive, remember, you just need to use examples. So just try it. It might seem like, wow, why am I doing this? But please, just give it a go. So let's start this. Choose a number less than 10. 9. Add 7. Just do the first one with me, and then the next two you can have freedom. Add 7. Multiply by 2. Subtract the original number. 23. Subtract 2. Subtract the original number. 21 minus 9 is 12. Let's do another one together, and then the third one will be for you. 2. Perfect. Add 7. 9. Multiply by 2. 18. Subtract the original number. 16. Subtract 2. 14. Subtract the original number. 12. Okay. So this sorcery needs to be demonstrated again in case 3. Try again. So the inductive reasoning, it doesn't really tell you how. It's like math magic. It's like sorcery. So now watch how we do this with the deductive case. Choose a number less than 10. X. Because it has to be in general for any number, right? And then this number less than 10, you can just say such that like x is less than 10. It's like a condition. You're going to choose x such that x is less than 10. Now we have to add 7. Hey, Will, please, pay attention, please. X plus 7. Is that too much out of the realms of our possibility? We could do that, right? Now here it gets a little bit tricky. You have to multiply by 2. 2 on the outside of x plus 7, because you need to take the result and times it by 2. Remember the order of operations. If you want that x plus 7 done first, you got to put it in a bracket. You can now simplify that by multiplying inside. What do you get? 2x plus 14, because the 2 has to do what? Distribute. Distribution. or expansion. Expansion, yeah, you're expanding the polynomial. Okay, now you have to subtract the original number. What was the original number? So you have 2x plus 14, take away x, which equals what? X plus 14. If you can do like terms, what's 2 apples minus 1 apple? 1 apple. That's the same here. 2x minus 1x, x. And the plus 14 had no other like terms, so it just stays. Now subtract 2. X plus 14 subtract 2 would equal x plus 12. Subtract the original number. X plus 12 minus x equals 12. No matter what. No matter what x you pick, you will always end up with 12. That is mathematical proof, deductive reasoning, or logic. The stuff above was all inductive, like it was just trying stuff out. So we have proved that whatever original number is chosen, the final answer is 12. Does the original number have to be less than 10? No. You can in fact use any number. Any questions so far? It's quite nice to follow along when I do it. It's another thing to try this stuff on your own. So don't be afraid to make mistakes. Keep trying. If it doesn't go so well, get help. Next page. Remember how we talked about how you would represent consecutive numbers? With like n, n plus 1, n plus 2? This is another one that you have to memorize. How to represent odds or evens. So, how do you represent an odd or an even in general? That's what this next part is. So, this is like in general. How can you guarantee that your number will be even or odd in general? 2n, where n is an element of the natural numbers. Do you guys remember what the natural numbers are? So the natural numbers are the counting numbers. They're the natural numbers. Like if you were a caveman and you were just a primitive human and you were trying to figure out your reality, what would you do when you went to pick up a few sticks? 1 stick, 2 stick, 3 stick. Maybe 1,000 years later you break it in half and you're like, ooh, half a stick. There's such things as fractions. But the natural numbers are just the counting numbers. And that's an infinite set. They go on forever. You could count until your little heart desired. 1, 2, 3, forever. These are the counting numbers. They're the natural numbers. They're natural because you use your fingers. 1, 2, 3, and so on. Now, if you took any natural number and then times it by 2, what would you get? I don't know. Let's try some inductive reasoning. 2 times 1, what do you get? 2. 2 times 2, what do you get? 2 times 3, what do you get? What is this list that I'm generating? The evens. This is the list of the even numbers. Why didn't the 1 show up? There it is. So, how could I get the odds? It's a good thing you were here for this lesson. How could I get the missing odd? How do I get 3? Add 1. How would I get 5? Add 1. How would I get 7? Add 1. And they put 2n minus 1, but you could always just go 2n plus 1 as well. 2n plus 1. That's what I use. I think it's because if you put in a 1, yeah, let's just go with theirs because it's better than mine. Theirs is better than mine. Put in a minus. Yeah, because it starts off at 1. Yeah. Good. Now let's use what we just figured out to determine if this conjecture, let's see if this conjecture is true. When two odds are added, their sum is always even. Let's try that inductively by just trying. Two numbers are added, and they have to be odd. You get an even. Let's try that. 3 plus 5 is 8. 7 plus 9 is 16. 1 plus 7 is 8. I could do this until I keeled over from dehydration. 11 plus 17, 28. You just have to add up two odds, and you should always get a even. Now, to prove that deductively, you have to add two odd numbers in general. So you have this, odd plus odd. How could you represent an odd number? 2n minus 1. Oh my gosh, come on. 2n minus 1 plus, we'll use a different natural number to get us started, so we have a different odd. That's two odd numbers in general. Do you want to see if it works? Like, just pick a number for n. Pick one. 4? What's 2 times 4? 8, right? 8, take away 1. So is that thing odd? Now you're starting to have a light bulb. Now pick a different number than you picked here. You picked n was 4. Pick a different number, like maybe 10. That's an easy one. What if m was 10? 2 times 10 is? Take away 1. 19. So this is how to represent two odds in general. Now add those up, collecting like terms. What do you get? 2n plus 2m, and then what? -1 plus -1. You owe me $1, you owe Leighton $1. Altogether you owe $2. So -2. Now what do we do with that thing? What do they all have in common? They all have a factor of 2 attached. You can factor that 2 out. Okay, so you have to factor it out. Now this is done. This proof is done. Why is this proof done? What is n plus m minus 1? That's just some number, right? Take any number and times it by 2. What do you get? So this is any number times by 2. What does that guarantee? Any number times by 2, it guarantees it's going to be even. So it's proof. No matter what values you pick, it's going to come out even. So hopefully after today's lesson you have a clear understanding of what's the difference between inductive and deductive. And the homework that follows, it might be challenging for some, but it's worth doing. It's a real test of logic.